Hi, we're going to talk about 9.3, tests about a population mean. A lot of what we talk about is going to be the same as what we did in 9.2, obviously with means, not proportions. And then the things that change about this test are going to be similar to what we saw in chapter 8. So what do we know about inference for a population mean? What does our sampling distribution look like? We know, we're talking about the sampling distribution of sample means. So all of these are X bars in here. The mean of the distribution is equal to the true mean. We know that the standard deviation is equal to population standard deviation over the square root of n. We also know, as we saw in chapter 8, that this is probably unlikely, right? We don't know about our population. We don't know sigma. So what did we do? We substituted in our standard deviation of our sample. And by doing that, now instead of the standard deviation of our sampling distribution, we have the standard error of our sampling distribution, which is the sample standard deviation over the square root of n. And if you recall, this change meant we're not actually working in that normal distribution. We are in a t-distribution, which has something, remember, called a degree of freedom, which is equal to n minus 1. As the degree of freedom increases, our distribution becomes more normal. So let's talk about how we check our conditions for inference. Really, nothing's going to be new or different here. This is the good part. We check our random condition. Of course, that would be stated. Normal, ideally, our central limit theorem would come into play where our sample size is greater than or equal to 30, and then we'd be happy. But if you recall, because we're working with that t-distribution, we are able to have a little bit of flexibility here. So if our sample size is between 15 and 30, of course, we want to plot our data. A skew is okay. We don't really want any outliers. And then if our sample size is less than 15, less than, we'll say, again, we want to plot our data. Oops, I wanted this to be a different color. We want to plot our data in both of these situations. And when our sample size is less than 15, again, we really want only the slightest skew. And I think maybe a note to make is kind of a skew is okay in this range, and just a little bit of skew is okay in this range. As we've talked about before, if they want you to do the problem, if it's a free response problem, it'll probably work out even with skew. And then independent, nothing is new here. Our sample size is less than or equal to 1/10 of our population. So let's talk about that test statistic. A test statistic, as we have seen before, tells us how far our statistic is from our null hypothesis. So in this case, it would be mu sub 0. And we have said before that a test statistic is equal to our statistic minus the parameter over the standard deviation of our statistic. So if we think about it in our 9.3, when we're looking at means, our statistic, of course, is an X bar minus our null hypothesis mean. And we would put it over the standard deviation of the statistic, which we talked about above. Sigma sub X bar is population standard deviation over the square root of n, but we came across an issue that we don't know sigma, so we can't actually substitute in this formula right here. We can't do that, so we are going to use our standard error, S of x over the square root of n, and because of this change, because of the fact that we can't actually use this, and we need to use the standard error, it shouldn't be surprising that our test statistic is going to be a t value, not a z value. That, again, should feel pretty normal because we did that a lot in chapter 8. We'll do these next two examples. About a classic rock radio station. They claim to play an average of 50 minutes every hour. However, every time you turn on the station, it seems like there's a commercial playing. To investigate their claim, you select 12 different hours during the next week and record what the radio station plays in each of these 12 hours. Here are the number of minutes of music in each of these hours. Notice that we are not given our sample mean. We are simply given the sample. I do know that our sample size is 12, and I know that the stated mean is 50. So our null hypothesis would be that the true mean is 50, and we believe that they don't play that much. We are saying we think that the true mean is less than this 50 minutes. They weren't asking us to state the null and alternate hypothesis. I just think it's helpful in this problem. We need to check the conditions. So for random, of course, we see that we are randomly selecting. Which is great to check our normal condition. Independent, our sample size is 12. That means we need to see at least 120 different hours we could have selected in a week, and that is a true statement. There are more than 120 hours in a week. So we're happy about that. And now if we want to check our normal condition, unfortunately, because our sample size is small, we do need to plot our data. I'm going to pause the video and enter my data into my calculator, and then we'll talk about that in a moment. Of course, I enter my data into my statistics area, and then I'm going to go to my y equals. I'm going to turn my stat plot on. We want to create a histogram, is probably the easiest way to see it. I'm going to select zoom 9, zoom stat, and I see my histogram. Now we notice it's not perfectly symmetric, and that's actually okay. If I want, I could change my viewing window a little bit, make our bins maybe smaller widths. Let's see if that changes anything. So I would go to my window and change my X scaling. So it's at 1.8. Maybe we make it 0.9. I'm making them half. So then I go to graph and I see, again, not a perfectly symmetric set of data, but it's not super skewed either. And realistically, if we're trying to do a problem like this, it's probably going to work. So I'm going to plot my data. I'm going to sketch this little histogram here, and I am going to say that there is a slight skew, but it is okay to use our T procedures. It is important to draw out your histogram here. Then they ask us to continue this problem by, well, we didn't, I guess, yeah, we did talk about this. In this last example, we were talking about that the true mean is 50 hours, where mu is hour, nope, not hours, sorry, minutes played. Minutes, the true average minutes of music played per hour. And they want us to compute our test statistic and p-value. So I know my test statistic t will be equal to x bar minus mu sub 0 all over s of x divided by the square root of n. Unfortunately, I don't know my x bar and s of x. In this example, they do not give it to us, but because we just entered our data into our calculator, we're able to get this pretty easily by going to stat, calculate our one variable statistics of list 1. Now I see that for my sample mean, I have 47.9 minus our null hypothesis, which is 50, all over my sample standard deviation, 2.81, over the square root of 12. When I take some time to calculate this, I get -2 0.59. This is our test statistic. Once we have our test statistic, we are going to calculate a p-value, or the probability that that statistic or more extreme happens. So we are looking at a t-distribution. It has a degree of freedom of 12 minus 1 of 11. We know a t-distribution is approximately, like, it's going to look like a normal curve. It's symmetric. I have negative 2.59 because it still has a mean of 0 and a standard deviation of 1. And I want to find the probability that I would get this t-value or more extreme in the direction of our alternate hypothesis. So of course we're doing less than negative 2.59. I can shade this here if I'd like. And how do I calculate this? Well, I can do it a couple different ways. One is to go to my t-CDF, just like normal CDF. So I want, actually, sorry, I didn't go to the right place. Not in statistics, I'm going to variables. Oh, and I'm actually going second variables. We want t-CDF. It's a t-distribution, and we want cumulative. The lower, in our case, is a very small number. Our upper is the negative 2.59, and the degree of freedom we said was 11. I can paste this into my what happened? Let's see. Oh, I did a minus sign, not the negative sign. That would make a very big difference. Here we go. We get my p-value. We now know that the probability of getting a t-value this small or smaller is 0.01 or 1%. We were not given a significance level, so we can't necessarily make a conclusion here, but if we had done a significance level of 5%, we would reject the null. We would say we have evidence to believe that this radio station is playing less than 50 minutes per hour. Tune in for the next example in a little bit.